The fifth presentation in Unit 1. It's called Accelerate Your Knowledge. Our quote is, "Real knowledge is to know the extent of one's own ignorance," by Confucius. Okay, the learning goals for this particular presentation are that you be able to algebraically manipulate the equation that we introduced in the last presentation. And that's this A equals VF minus VI over delta T. And so we want to be able to manipulate that to solve for one of these unknown variables like T or VI. So, what we already know, what we've talked about in the previous presentations, is that the slope of a velocity versus time graph will give you the acceleration. And we can actually take that and we can formalize that into the equation A equals VF minus VI over T. This is the expression we've traditionally used to solve for the acceleration. Now, what we do want to look at in this particular presentation is, what if I'm not interested in acceleration? What if I can somehow measure this directly and I want to know what the initial velocity is? So that's where algebra is going to come, and it's going to make our life a little bit easier. So the first thing we can say is what we learned in the lab. In the lab, we learned that velocity can be predicted given the acceleration and the time. Whenever you have a static situation, or excuse me, a situation in which the acceleration is static, you can go ahead and you can solve for other variables there. Your brain does this whenever we catch falling objects. Whenever an object falls, it is accelerating due to gravity. Whenever it accelerates, it's got a constant acceleration, so your brain does these calculations on its own, although it's not a conscious thing. So, using a velocity versus time graph, the first thing we can do is we can obtain velocity and time as well as acceleration from this graph. If you were to look at the velocity versus time graph, we can determine what the initial velocity is. So let's say I want to know the initial velocity between 5 and 10 seconds. Well, the initial velocity would be the velocity at 5 seconds, so I'd look here and I'd say, wow, the initial velocity here is minus 3. And then I could say the final velocity is the velocity at 10 seconds, which is 2. So I could say the initial velocity is minus 3, and I could say the final velocity is 2 for this time frame. Now, if I wanted to look at the graph overall, it'd be something a little bit more difficult, and you can see that here. You actually go to the particular time. In this case, I went to 7 seconds. I drew a line straight up, then I drew a line straight across, and I find out that the velocity was 2 at 7 seconds. You can also find the initial velocity. If there is no time frame given, the initial velocity is the time at t equals 0. So in this case, the velocity at t equals 0, it starts at the point 0, 0. So at a time of 0, the velocity is 0. So what we get from this is, on a velocity versus time graph, you can find the initial or final velocity simply by reading the graph. You can do the same thing for final velocity. Okay, if you know what the final velocity is, you go to that particular time and you read the graph across. Okay, so now, in this particular question, it says, what would be an appropriate title for this graph? Remember, we title our graphs with the dependent and independent variables. So we want to make sure we follow the same format for every single one here. So when we do this, we want to say, okay, what is my dependent variable? And it's velocity. Versus, what's my independent variable? That's the one on the x-axis, which in this case is time. And then you need for something. So this is velocity versus time for a car, or for a toy car, or for a ball rolling along a ramp, or something along those lines. But you should say velocity versus time for, and then you can make up the rest of the title based on what the experiment is. On this one, it says, what time will the object be at 3, it should say centimeters per second, because we're at centimeters per second right here. So we want to know what time the object will be at 3 centimeters per second. So when you look at this, it says we've got to go to 3 centimeters per second, and that's right here. So what we do is we read this across, and we say, okay, this is the entire time that it's at 3 seconds, and then we draw a line down. And since it's in between the 0 and the 1, we have to make a decision and say, okay, what is this? What's the estimate for this particular value? And if you were to go straight down using a ruler, it looks to me like it's halfway in between 0 and 1. So I would say this is at 0.5 seconds. Now, you could additionally use other points. Anywhere along this 3 centimeter per second line would be a valid answer. So if you were to say 1 second or 2 seconds, those would be equally valid answers. Now, if it says, what time does the object first reach 3 centimeters per second, then this would be the only answer. But when it says, what time is the object, or will the object be at 3 centimeters per second, all of these are valid answers. The next one says, what is the velocity in standard units at 3.5 seconds? So the first thing we do is we come here to 3.5 seconds. We draw a line down, and then we draw a line across. And whenever you do that, we get a velocity of about, it looks to me about minus 1.5 centimeters per second. Okay, so we have minus 1.5 centimeters per second. Now we want to convert it because we want to be in standard units. The standard unit that we have for velocity or speed is going to be in meters per second. Well, now the seconds matches up. I'm in seconds and that's good, but what doesn't match up is meters and centimeters. So what I'm going to need to do is convert the centimeters value into meters. To do that, I say there are 100 centimeters in 1 meter, and now I'm in meters per second. You multiply it across and you get a speed, or a velocity in this case, of minus 0.15, sorry I forgot a zero there, 0.015 meters per second. That's our velocity in standard units. So this right here, negative 0.015 meters per second, is the same thing as minus 1.5 centimeters per second. This next example says, what time does the object reach the maximum distance from the starting line? This one is a real tricky question because what you're trying to do is you're trying to talk about displacement and not, or how far it is, not velocity and not acceleration. So what you should realize is that if you were to look at velocity and time, if you were to multiply those two values together, like meters per second and seconds together, you would get meters. Well, when you multiply something together, that's the same thing as finding the area of a shape. So at this point, you want to figure out where its area is the maximum. In other words, where is the positive area over the x-axis the greatest? So if you were to look at this, I've got this area right here, this shape right here. It's a trapezoid. Okay, I could figure out the area if I wanted to, but it's not actually asking me for what the area is, it's asking me for the time. I also have this area right here, which we're going to go ahead and change to a different color because it's below the axis. Okay, what this graph is indicating is that I'm moving in the forward direction, and then when I get here to 3 seconds, I'm actually going in the reverse direction because my velocity goes negative. Remember, negative velocity indicates a change in direction back to where you came from. So because of that, this area below the x-axis is actually reducing the distance you are from the starting line. So if you were trying to figure out where you're at the maximum distance, that's actually right here at 3 seconds. Now, if I asked you to go ahead and say, what is this maximum area? We would need to find the area of this particular trapezoid. So whenever you find the area of a trapezoid, it's equal to area is 1/2 the base 1 plus base 2, and then times the height. Well, our height in this case, the highest that it goes from 0 to 3. So my height is really easy. I can say 1/2 and then 3. The base 1 is really easy. It starts here at 0 and it goes here to 3. So my first base is 3. The second one that's a little bit trickier to see is this top base, this base 2. And what I would say is it ends at 2. That's pretty easy to see. But if you look, it doesn't quite make it to a whole number there. So I have to estimate once again. And I'm going to say that that's 0.5. So 3 plus would be 1.5 because it goes from 0.5 to 2. So 3 plus 1.5 divided by 2 times 3 is how you would find the area of this particular trapezoid. When you do that, it ends up being about 6.75 centimeters squared. As we discussed in the second video in this unit, algebra makes your life a whole lot easier in that you don't have to remember a multitude of equations. Instead, you can remember one and rearrange it. So algebra actually makes your life easier because sometimes you're not interested in the velocity, or you're interested in velocity and not acceleration. So there's no need to memorize multiple equations if you can do algebra. So remember, when we rearrange the equation, we circle what we want to isolate and we go from there. So an example of this is, if we start with our original equation, if we can multiply both sides by delta t. Because remember, you can think of it like this. Let's pretend this divide isn't here, and let's put this delta t down here. If I were to multiply both sides by delta t, whenever you do something to both sides, you don't change the value of the equation. But what I've done is I've now set it up where these two things cancel out. So I get a delta t equals vf minus vi. So this allows me to go one of two ways. I can actually take this thing and I can solve for VF, I can solve for delta t, or I could even solve for VI if I wanted to, but generally that's not one thing that's solved for, because usually in most situations you have the initial velocity of something. So option number one is I would add VI to both sides. Remember, when I add VI to both sides, it doesn't change the value of the equation. Well, minus VI and plus VI, those two values will cancel out, leaving me with VI plus delta or plus A delta t equals VF. This is a very common version of the equation that you see in many physics textbooks. Another version of the equation is if we take this thing and as if instead of adding VI, if we divide both sides by A. Whenever you divide both sides to A, once again, you've done the same thing to both sides of the equation, and because of that, you haven't changed the value of the equation, but instead what you've done is this cancels out, and you now have delta t equals VF minus VI over A. So it's just showing you how you can rearrange this particular equation to solve for four different variables. You can solve for A, you can solve for VF, you can solve for delta t, and you can solve for the less common VI. So what does delta mean in the equation? Remember, delta means change, but more specifically, more than change, it means final minus initial. So for example, if I asked you to say, what's the delta V, it would be VF minus VI. If I asked you to solve for delta T, it would be TF minus TI. If I said, what's your change in your grade, it would be your final grade minus your initial grade. Okay, delta always means change or final minus. And the next one, it says, a car is initially at rest and accelerates at 4.5 meters per second squared for 5 seconds. How fast is the car moving? So remember, whenever we do these types of questions, we always want to use the guess method. So what we do is we say, okay, I've identified this. I'm going to go ahead and underline my numbers, circle how fast I'm going, and I'm going to start to apply the guess method. So I want to identify my given. I'm going to say initial, final, the displacement or the distance, the acceleration, and the time. And I'm going to look at this and I'm going to say, okay, initially at rest, that means its initial velocity is 0. Then I'm going to look at this next one. I'm going to say, okay, 4.5 meters per second, that's a unit of acceleration, so I'm going to say 4.5. Then I'm going to say time is 5 seconds. And then I'm going to say, how fast is the car moving? That lets me know that I am trying to solve for the final velocity. At this point, I know that I'm trying to solve for the final velocity. My equation is A equals VF minus VI over delta t. But I have to rearrange this particular equation to solve for final velocity. So you could remember what the equation is from the previous slide, or you can go ahead and get practice algebraically rearranging it. That's what we're going to do here. We're going to multiply both sides by delta t. Actually, let's change colors real quick. We're going to multiply both sides by delta t. And when we do that, you can see what I've done algebraically is the same on both sides. That's going to cancel this delta t out, and it's going to leave me with the equation A delta t equals VF minus VI. The next step is I'm going to try and solve for VF, and when I do that, I'm going to add VI to both sides. Once again, it's in the same color, so you can see that I'm doing the same thing to both sides. That's going to cancel this term out. And so what that's going to leave me with is VF equals VI plus AT. So I just switched the sides because it's more common to write the variable on the left that you're trying to solve for. So now you can go ahead and you can solve. You can plug in your numbers, and I could say, okay, this equals 0 plus 4.5 times 5. And whenever you take 4.5 and multiply it by 5, you end up with a value of 22.5 meters per second. Now, some of you at this point are saying, okay, well, can I just plug the numbers in and then solve? And yes, that's absolutely a valid thing for you to do. If you are more comfortable just plugging the numbers in and solving, you can do that as well, and we'll show you that on the next example. This next one says, how long will it take a car to accelerate from 0 to 60 miles per hour at an acceleration of 2.8 meters per second squared? So in this case, I'm trying to solve for how long. That's going to indicate a time. I know that from 0, that tells me what my initial velocity is, and then 60 miles per hour, that lets me know I'm going to have to convert, but it's a final velocity. And then also I have an acceleration right there because it's in meters per second squared. Okay, so we're going to go ahead and assign everything to variables. We're going to say VI is 0. We're going to say VF is 60 with a little star right there because we know we're going to have to convert it. We know that the acceleration is 2.8 meters per second squared. And then finally, we know that the time is something we're trying to solve for. So in this case, I'm going to go ahead and convert 60 miles per hour, which is something you should be familiar with from earlier in this unit. If I want to convert 1 mile, there are 1,600 meters in 1 mile. And then I can go ahead and say, okay, in 1 hour, there are 3,600 seconds. Or you can do 1 hour, 60 minutes, 1 minute is 60 seconds. And when you multiply that out, you end up getting a value of about 26.8 meters per second. That is the velocity that's the equivalent of 60 miles per hour. So now we have our equation. I'm going to go ahead and just change colors so it's easier for us to distinguish. Here's our equation. A equals VF minus VI over T. Instead of actually trying to plug in and rearrange and then solve, I'm actually just going to plug the numbers in and show you that it works both ways. So in this case, I'm going to have 2.8, which is my acceleration number, is going to equal to 26.8 minus 0, okay? Because in my initial velocity is 0. All of this divided by t. So now at this point, you should realize that you can't really solve this at this point. So you'd say, okay, 2.8 is equal to 26.8 over t, because 26.8 minus 0 is still 26.8. Now, one trap that people get into at this point is they will take this and divide it by 26.8 and say, oh, I got t by itself. Yes, but t would be on the denominator, so you can't do that. You are still going to have to do a little bit of algebra to go ahead and get the t on the top. When you do that, you end up crossing those terms out, and you get 26.8 equals 2.8t. You divide both sides by 2.8, and when you do that, you get t equals 9.57 seconds.